Take a look at the universe around us today. It is highly organized. We see massive, mature galaxies defined by elegant spiral arms and smooth, glowing ellipses, all packed closely with billions of steady burning stars. But the universe immediately following the Big Bang looked nothing like this. In its earliest days, space was filled with a uniform, almost featureless fog made entirely of pure hydrogen and helium gas. That presents a massive evolutionary gap. We have to figure out the physical mechanism that took a completely uniform fog of gas and condensed it into the highly structured, organized Milky Way we live in right now. The missing link between those two extremes is a structure known as a protogalaxy, sometimes called a primeval galaxy. A protogalaxy is essentially a massive, chaotic gas cloud in the process of a violent gravitational collapse. You won't find the neat, predictable shapes of modern galaxies here. They are clumpy, distorted, and irregular. By pulling that raw gas together and forcing it to collapse, these primeval clouds acted as the vital transitional phase that forged the structural order we see in the cosmos today. Cosmologists explain this structural assembly through the cold dark matter theory. This theory maps out a bottom-up hierarchical process where small, simple components merge to build larger, complex structures. Interestingly, this assembly line does not start with stars. The foundational building blocks of our universe were actually invisible clumps of dark matter. Because dark matter has massive weight, it creates deep gravity wells, pulling in surrounding hydrogen and helium gas and funneling it into highly concentrated pockets. As the gas falls into these halos, intense compression causes it to heat up dramatically. And because stars require cool, dense material to ignite, they absolutely cannot form an intensely hot, expanding gas. This initial gravitational heating creates a steep physical barrier to galaxy formation. To overcome that heat barrier, the raw gas must find a way to rapidly cool down. Only then can it collapse tightly enough to spark nuclear fusion. The gas manages to shed this heat by radiating energy away as a specific wavelength of ultraviolet light. This cooling process creates massive, glowing reservoirs of gas, known as Lyman alpha blobs. Once the gas bleeds off enough heat to reach a highly dense state, the massive cloud violently fragments, breaking apart into smaller, tightly packed pockets. That sudden fragmentation acts as a massive catalyst. It creates a volatile starburst environment, igniting new stars at a frantic, highly concentrated rate that completely dwarfs the star formation in a mature galaxy. These newly ignited bodies are known as population 3 stars. They are the very first generation of stars in the universe, forged entirely out of primeval hydrogen and helium, without a single heavy element, or metal, inside them. The specific ability of that raw gas to radiate heat and splinter into fragments is the exact trigger that turns a dark matter sinkhole into a brilliant star-producing engine. Those massive population 3 stars burned hot and died young in massive supernova explosions. When they exploded, they seeded the surrounding primeval gas with the universe's first heavier elements, like carbon, oxygen, and iron. This comparative matrix tracks that evolution. On the left, the chaotic metal-poor protogalaxy undergoes rapid gravitational collapse. As early stars enrich the chemistry with metals, the extra mass causes gravitational settling, shifting the structure into the mature, near-equilibrium state seen on the right. The pristine, metal-poor chemistry of the early cosmos was entirely incapable of forming a rocky planet. You need that heavy, complex chemistry from repeated star deaths to build environments like our own solar system. The complex chemistry of Earth and the precise orbital structure of our galactic neighborhood were directly forged in the violent, chaotic life cycles of those primeval protogalaxies. Proving this physical process requires us to use the speed of light to our advantage. Because light takes time to travel through space, looking at objects at the extreme edge of the observable universe literally means looking billions of years into the past. The core challenge in looking that far back is the expansion of the universe itself. As space expands, it stretches the light traveling from early protogalaxies, pulling it into longer, redder wavelengths, a process cosmologists call high redshift. Because of that extreme stretching, the visual evidence of protogalaxies is pushed completely out of the visible light spectrum. They exist almost entirely in the infrared spectrum, often hidden behind thick walls of cosmic dust. To bypass that physical barrier, engineers built the James Webb Space Telescope. It was designed specifically with large gold-coated mirrors and incredibly powerful infrared sensors to cut through the dust and capture those stretched redshifted wavelengths. JWST is capturing the dim reddened light of the very first galactic structures forming roughly 200 to 500 million years after the Big Bang. By utilizing the physics of light and specialized infrared technology, we aren't relying purely on theoretical models. We are actively watching the first protogalaxies piece themselves together in real